Okay, so let's talk about um first of all, let's start the topic, which is of course quantum mechanics, not the topic, field, you will say. So what we will be talking about today is the operators in quantum mechanics. Okay, so operators are how there are many different kinds of operators in quantum mechanics, and you will be seeing all them very often in the mathematics of quantum mechanics, even the theory of quantum mechanics. So like there's Hamiltonian operator, then there is this identity operator and projection operator, identity operator are little like it's the same, because and so like even though some operators change the state uh, of the state in that area, and some don't change the state as well. So it depends on the operator what kind of function that operator does. So if I want to define operators, the operators in general, it's a mathematical identity, an identity that acts entity that acts as a quantum state. Okay, like in the Hilbert space, the Hilbert space can be of your own, like how big or how creative you want your space to be. And now what the main purpose of operators is to get a physical information. By physical information we mean the experimental data. experimental Experimental data. Okay, now in experimental data, we can do it by observations. Because in quantum mechanics, the observation is measurement. Observation is measurement. Okay, now what we mean by measurement is that if let's give an example of measurement, like observation. If we have light, okay, and that light has uh, right now it has both electric and magnetic field. Okay, but the moment an observation is made means we put a polarizer, which polarizer, let's suppose a vertical polarizer. Sorry for this, wait. Okay, now after this is here we call it a measurement. Okay, now this measurement, what it will do is, we're talking about observations as measurement, right? So here in some way what we did is that we made a measurement here, and this measurement caused light to now only have horizontal part, horizontal oscillation only. Now in some way we changing change of sorry I'm change change of state. So because what I mean by change of state is here it was uh, vertical, horizontal, but then it turned into a horizontal only. Okay, so that's what I'm talking about, change of state of light. Now when we talk about operators in particular, what type of operator we'll be talking about are Hamiltonian operator, no, sorry, Hermitian operator, mission operator. Okay. um Hamilton, or it's better to say Hamiltonian operator. Hamiltonian operator. Now, in Hamiltonian operator, it's about energy. Okay, it's about energy. It's we're talking about energy of a physical quantity in a given situation. So if I want to write the Hamiltonian um, operator, it will be like this, and they all are acted upon by wave function, and so we get E n of lambda. Oh, sorry, not lambda, wave function. Now, this what it does is energy of operator, energy of a physical quantity in a different situation. So because it depends on situation to situation. In some situation it will be different, and some it will be different. Now, um, here this is what we call the Hamiltonian operator. This is the Hamiltonian operator. Okay. We will not go into depth of what they are. We'll just focus on our main fact. Okay. Now, I will be as simple as we can. Now, then second one is uh, identity operator. The identity operator is very like different from the other operators, as the main thing is it changes nothing. It remains, the state remains unchanged. Okay, meaning I acted upon wave function gives us that same thing, no change. Even here I'll give you one more example by using commutators. This is sorry, x and p, and what will happen is I of x and I of p. This is how it is actually, and this comes down to I is this and I. Yeah, that's how it is. Look, no change. This I is literally nothing. Here, since these are operators, we can't put operators on operators. So here we put I. That's the identity operator. Okay. So in identity operator, there is no change uh, in what we know. By the way, here I is a complex number and h is a reduced Planck constant, which is h is equals to, wait, let me write on the top. H is equals to h bar is equals to h over 2 pi. That's our reduced Planck's constant value. We know the value of h, which is 6.626 times 10 to the power minus 34 joule second. And you can get, if you get this, put this apply here and do it to over 2 pi, you will get the reduced Planck constant. And yeah, okay, so and then this was identity operator. Identity operator is just, we are it's actually the equation. If I want to write for the equation of identity operator, it is actually summation I p of I. Now here, what is p? P is projection operator. Projection, okay. Now what this does is it writes like the possible outcomes, possible outcomes, okay, all possible outcomes. Let's suppose if we have a certain state, we are given a certain state, and there can be many ways to represent that certain state, and even this to use this, there's one sphere which we use is called block sphere. Block sphere, if I'm saying it correctly, block sphere, something like that, okay, which looks like this actually. Okay, and each part over here represents a state, and this as well. What was it? What was the other states again? Z, I. Now here right now I'm just going for random, and 0, no, 0 1 and 0 0. Okay, this how if we represent this state over here, it can also be represented over here, here, and I think here. Yeah, there are many ways to represent this state. Okay, and these are possible ways to express, which is shown by projection operator, and the use of this is mostly in QST. QST is quantum state topology. I have seen this in quantum state topology, the use of projection operator. There are many other uses as well, but the application is for this quantum state topology. Now, identity operator, other than identity operator, there's one more operator known as linear momentum operator, or only linear momentum. We don't write operator with it. Now, this is one of the interesting one, which is used in one of the famous equations, Schrödinger equation, or like, yeah, it's one of the famous equation in quantum mechanics. So it goes by P of lambda is actually in broken form, it's I h bar, and this is one more operator which we'll study later, and this. Now one more thing, we have seen wave function, wave function, even here wave function. What wave function does is that it puts it in multiple probabilities, so that, because in quantum mechanics nothing is definite, it's all about probabilities, okay. Now, and that's why we put wave function. So we are given a set of probabilities, and from which we get the values chosen from them, okay. Now nothing like this, not this is a momentum operator, or linear momentum, how you want to say it. Linear, by the definition, linear momentum, you might have already know, it's like one dimensional operator. And then there's one more operator which is I was not supposed to say about it, but like, okay, let's talk about it as well, which is known as angular momentum operator, which is like a little bit different about from linear momentum. In linear momentum, we are talking about only one dimension, but in angular momentum, we talk about all three dimensions. It's a three-dimensional operator, which goes by Lx is equal to I h bar with I and minus in the middle in the start. This, and that's a partial derivative, again partial derivative, and it goes on. Okay, and since we're talking about three dimensions, it will go on, and it's called, what was it called? Yeah, angular momentum operator. Now this z, y, z over here are showing the dimensions we are looking at. Okay, they all are dimensions. Now we'll not go into depth of this one because it's not that important for our topic. It's like complex one, so we'll just focus on identity. And one more operator which I have to talk about is there's one more operator which is the, what was the name of that operator? Uh, Actually, over here, oh yeah, I think that's it. We don't have any more operators. Now, there's one more thing I want to talk about um, is that what was it? When we write this equation over here, when we wrote this equation over here, we know that these are called commutators. Commutators. Okay. Now, what these commutators do is they are written like this: A and B, which can be written as AB plus BA. Okay, these are called commutators, and this is mostly used for uncertainty principle. This is how uncertainty principle is derived from. I have made a video on it. It was like okay. I have made a video on derivation of uncertainty principle. Now this over here is one of the way we can represent this operators, like this commutators, and the use of commutators, or the use of commutators is very interesting because they play like a very well. Basically, all of quantum mechanics has their own fundamental role plays, like operators and the commutators, which together make up the whole system. But they also, like, even when we talk about linear momentum, the operators, in fact, in a particular operators, what the operators do is, they operators and commutators, they are transforming the way we look into the at quantum mechanics. They change the everyday life of like everyday measurements of quantum mechanics. Now there's, I just remembered one more operator which is known as lap sorry lap Laplacian operator. I don't know how to spell this guy. Now here, it's, I should have talked about the other one first, the other which is known as uh, sorry, I forgot about this operator, which is known as gradient operator. Okay. Now what gradient operator does is, yes, you might have heard, like, thought correctly from the word gradient operator. We're talking about dimensions. Okay. Gradient operator is gives us what dimension we're talking about. Okay. We are spatial dimension. Spatial dimension. It just gives us an overview of when we are looking at a wave function, and when we look at a wave function, and when we look carefully into the wave function, we're looking at in which dimension does, at this point, like at this dimension or this spatial dimension, what's the change in curve? Change in curve. Okay. Now here same thing. Lepton or how do I like pardon about this operator. The thing is that it's the second order of the first operator. By second order, we all know about the derivation, so it's the same thing as that, and it's written the same way: d over dx square, d square over dy square, and d square over dz square. So and this is used for there's more about this operator which is used in the famous equation for which is used for energy findings. Energy findings in Hamiltonian equation. Hamiltonian operator. Okay. Now I'll write the equation in which it's used, which is the famous equation, Schrödinger equation. Okay. Because now, oh, it's the best part here. I just thought of something that when we have just talked about the operators, right? And if I write all these operators, which is Hamiltonian operator, not identity, and linear momentum operator, and the gradient operator plus the second form of gradient operator, which is this one, comes in this equation, and plus we have one more operator, one more point here, which is the potential difference, which is difference, and that potential difference varies with what we're talking about. So the general form of the Hamiltonian equation is H equals K plus GPE for the labor terms. We all know what is K, we all know what is GPE, which is potential difference, potential, not difference, energy. We're not going to electrical physics. And so this one is kinetic energy. Okay. And so this equation can be expanded into H equals P square over 2m plus Vx. V for in terms of x. Now this can be further simplified to the operators which we have, which is the Hamiltonian operator, Hamil, and the which other operator is this? This is the momentum operator. Hamiltonian operator. Okay, so what are they? P is equals to I h bar d this, and h is equals to I h bar d over dt, and both acted upon by wave function to give a. Why do we apply wave function to get a physical 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 information, physical reality information, useful data, and it's terms of like this actually. It's not like that. It's this actually. Yeah. Now here the this is this is another operator which is inside the momentum operator, which is known as we already talked about it. The second in simple form is this. It can be this as well. Depending on what dimension we talk about, so we can change it, or we can look at all the dimensions, and it shows the change in wave function. We might just want to finish the topic fast. Now, let's just finish with the equation. Then that's it. That's the ending point. We'll not talk about commutators anymore. Commutators will leave for today. I'll talk about it in the other video. Now, if I want to now, I'll write the full equation, the full derivation actually over here. H is equals to P square over 2m plus v of x, and h is equals to sorry I h I h square over 2m, as well as the gradient operator square plus v of x, and then h, then this gradient operator can further be divided into uh minus h square over 2m. Oh no, sorry, I doesn't come here, sorry, since because negative I is I actually 1, so we don't write negative I square, and I don't have to go through the working, so because you guys will know already why it's 1 only. So uh, and this becomes this square d of square d of z square d upon dz derivative, and then we have v of x, and the final touches, which is okay, now we'll have the final touches, which is I, the Hamiltonian operator replaced with this, is equals to minus h bar square over 2m, and this whole, okay. And now finally what we will do is, yes, we will replace this whole equation in terms of, wait, why am I repeating right again? It will take a lot of time to write. It's a huge equation, and this equation now becomes duplicated, get down. Now the only things we have to add now is the wave functions, which are this. I'll write this whole thing as like this, and wait, how do I write it? Acted upon by wave function, and this wave function normalizes, it can be normalized to sum up to 1, and yeah, that's it. And what else? Is there anything else we can talk about? I missed. I think I covered everything for the operators. Like, there are many operators, by the way, and I just covered some of the operators here, with the simpler ones, of course. And like one key operators as well. There are key operators, and this is where the Schrödinger equation they were there, and and in the Schrödinger equation we have the operators which we can see over here, and in by the way, over here one more thing, these are the types of coordinates which we can have. There are multiple other coordinates as well which we can replace with them with, and there are this and this. These are different kinds of coordinates, but it depends on what type of coordinates you're working with, you will replace them accordingly. But these are called now these are the simple coordinates which we use in our daily life mathematics. And yeah, thank you.